Hello everyone, the problem that we're looking at today is 2018 US Open Gold Problem 2 of milking orders, and you basically have a bunch of arrays and you're trying to make a permutation of 1 to n that satisfy as many of these arrays as possible, and no, it's want to satisfy as many of the first contiguous arrays as possible. So for example, you have this many, so you want to set, if you can satisfy the first one and the second one, that's better than only satisfying the first one and the third one, because you want to satisfy as many as possible while prioritizing the earlier appearing arrays. And if there's several permutations that satisfy the same number of arrays, then you take the one with the lexicographically smallest order, of course. And there is at most n 10 to the fifth power. Also, I realized that I didn't actually summarize the problem well enough, so here is the official wording. Farmer John's observations are prioritized, so his goal is to maximize the value x for which his milking order meets the condition outlined in the first x observations. So pause the video first and think about this yourself. Okay, I was pretty oars back when I did this problem because on the first look, I realized that was binary search. And I mean, it makes sense now if you tell me it's binary search, but I can't really think of binary search just by looking at this. Anyways, is binary search. And how are we going to do this? Well, first of all, obviously we connect edges because each cow prioritizing over the next cow just gives a strong graph theory vibe. However, if there's loops, we use topological sort to rule out that possibility because, well, if there's loops, then we have to decrease the binary search amount. That's how we check with binary search. So if the first x doesn't have loops, then we can go further. If the first x does have loops, then we decrease the mid in the binary search. And we also have to decrease we had to find the topologically smallest. So, no, not topologically, lexicographically smallest. So we still use topological sort. However, we increment a priority queue in which we prioritize the cows with the smaller lexicographical order along with topological order. And that was the only kind of big brain part of this problem, not even that big brain. So let's check out the process. So first of all, we make n vectors, no, m vectors because each vector is its own thing. And then we binary search, checking whether there is loop in the first x. Now is how many is whether it's possible to satisfy the first now restrictions. And we connect edges according to the restrictions. Use topological sort if the in degree is 0. If num_y is if the in degree is that's just topological sorting. Everyone knows how to do that. If there is edges, we return 0. Okay, now we have to also sort out what the final order will actually be. So that's why we still have this huge chunk after the binary search because we have to do topological sorting all over again. However, this time we use a priority queue. And of course, priority queue is prioritize larger elements, so we wanted to prioritize smaller elements. So we multiply everything by -1, and then we print out the topological order. Okay, so that is it for this problem. It's kind of big brain. First of all, you have to notice it's binary search, and then you have to notice topological sorting, but also using priority queue. That's pretty big brain. And I was really orders back then, 3 hours and 40 minutes. Like, holy cow. Anyways, thanks for watching. See you tomorrow. Okay, for the grind report today, first of all, I know there wasn't a grind report yesterday, and that's because I didn't grind yesterday. It was New Year's Day and stuff happened, so sorry. But anyways, today I did, let's see, 2020 December, I believe, problem 3, gold of square pasture. And as we all know, 2020 December was a very weird year for gold because the cutoff was 600. And even USACO itself acknowledged that this contest was extremely hard. However, that's for 2020. For 2025, this is just regular level problem. However, I could not only not solve this, but even after looking at the solution, I had to like debug for like an hour straight, along with coding for another maybe 30 minutes. Anyways, it does give us a rather big takeaway though, because now we know a new method of counting in counting theory, I guess. Usually I knew two methods such as contribution, like how many sets each element contribute to in counting problems like these, counting number of sets. That's contribution, and of course, obviously just brute forcing every set, whether it's possible. However, here's a third method. Enumerating two extreme values and then using a two-pointer to find how many other extreme values can pair up with these extreme values. And the number two extreme values that we're enumerating varies by problem. In this problem, since the time complexity is n cubed, we used n squared to enumerate two of the extreme values, and then use another n time complexity to do two pointer, and then find how many possible third extreme element of this set there are. In this case, we enumerate where the left and right end are, the two extreme values, and then use the two pointer to find how many top and bottom values there are possible. So yeah, pretty easy, but it's a new idea. So I would say, well, not good grind, but I mean, at least I'm doing stuff unlike yesterday or the day before. Thanks for watching. See you tomorrow.